Good evening, professors. We will be presenting assignment 2. So we have Brendan, Xiang, Joe, Ryan, Darius, and me, Adam. So I'll begin with question 1, seam carving using dynamic programming. So seam carving is a content-aware image resizing technique. Instead of simply scaling or cropping the image, it removes the least important pixels by analyzing energy values. So the first step is to calculate the energy map, which tells us the importance of each pixel. We start by converting the image to grayscale, so we only work with single intensity channel. Next, we compute the image gradients with sober operation in both the X and Y direction. These gradients highlights edge and areas with strong textures. Once we have the energy map, we use dynamic programming to find the minimum energy seam. For vertical seam, we build a cumulative cost matrix that stores the lowest energy to reach each pixel from the top of the image. The cost is updated using a reoccurrence relation that chooses the minimum of the 3 possible predecessors. After filling the dynamic programming table, we backtrack from the lowest value in the last row to retrieve the final seam path. For horizontal seam, instead of rewriting the algorithm, we transpose energy map and reuse the same vertical seam logic. After identifying the minimum seam, we remove it by shifting pixels to the left. This reduces the image width by 1 pixel without distorting important content. And because of removing a seam changes the image, we repeat the entire process, energy map calculation, seam finding, and seam removal. So right now I'll show the application. So in our code, we can run the application and then we can load an image like Moreno. Choose dynamic programming and show the seam. So we want to seam carve it to 1000 by 900. And then we can run the seam carving. So while it's running, there will be seam carve of the image and we can actually output later on. So while it's running, we'll present question 2.
So given an n times n image where m is the number of rows and n is the number of columns, the number of possible seams that exist in an image grows exponentially in m, assuming n is more than 1. As we move down each row, we have multiple choices for selecting the next pixel in the seam. If the current pixel is on the edge, then there are only 2 possible choices for the next row. If it's an inner pixel, then we have 3 choices. Because we are making one of these choices at every row, the number of possible seams grows exponentially with the height of the image. And at the lower bound, there is 2 to the n-1 power possible seams for an image with m rows. Next, we will relate seam finding to subproblems. When we find a seam that has the minimum total energy, we need to know the minimum energy seam ending at the last row. And to find that, we need to know the minimum energy seam at the second from last row. And to do that, we need the minimum energy seam at the third from last row, and so on. So the problem naturally breaks down into a top-down approach. And for each pixel, we compute the minimum energy seam that ends at that pixel. For the first row, which is the base case, the total energy is just the energy of the pixel itself. And after the first row, we use recurrence, where the minimum energy at pixel ij is its own energy plus the minimum energy of the 3 pixels, either the pixel directly above, the pixel at the top left, or the pixel at the top right. And this dynamic programming approach lets us solve the large problem of building up solutions from smaller ones without having every possible seam. Next, I'll pass on the time to Joel.
Okay, thank you, Xiang. So for question 2b, we are looking at how the gradient of an image is computed and by whether using the divide and conquer method will improve the efficiency of this process. So as explained by Adam just now, in seam carving, we compute the energy map and we use the 3x3 Sobel filter to measure how quickly pixel intensities change. So this is also done through direct convolution, where the 3x3 kernel slides across the entire image. Because the kernel is so small, it gives a time complexity of OMN, where as told by Xianxiang, M and N is the row and column of the image, and is fast in practice. Now let us compare with two divide and conquer approaches. The first is fast Fourier transform, also known as FFT-based convolution. FFT converts the image into frequency domain, multiplies, and converts it back using the inverse IFFT. This results in the time complexity of OMN log Mn, which only becomes faster when the kernel becomes very large. For example, kernel size of 50 by 50. This is due to the overhead that FFT produces, but since for seam carving we are using the Sobel filter, which is a tiny 3x3 kernel, FFT ends up being slower than direct convolution. The second approach is the recursive and divide conquer convolution. This method splits the image into smaller regions and processes each recursively, but each pixel still needs to be convolved with full kernel, so which results in an overall complexity of OMN k square, where k is the number of subproblems it divides into. So this introduces recursion and merging, which gives extra overhead and makes it slower in practice, especially for smaller kernels. Hence, when we compare these methods, we can see that divide and conquer techniques don't always provide efficiency benefits for seam carving, and they only help for large kernels, which is not the case that we are talking about. Since seam carving repeatedly uses small 3x3 filters, direct convolution in the end still remains the fastest and most efficient approach. Now I'll pass on my time to Darius to talk about the greedy algorithm.
Thanks, Joel. Now that we'll talk about how seam carving in dynamic programming works, greedy algorithm is pretty much the same for the first and last step. I'll focus on the step in between, which is how we actually find the minimum energy seam using the greedy algorithm. Once the energy web is ready, the goal is to pick a seam that has the lowest total energy. For a vertical seam that reduces the image width, we start at the top row and choose the pixel with the smallest energy value. From there, as we move downward row by row, we only consider three possible neighbors: the pixel directly below, the left diagonal, and the right diagonal. Out of these three choices, the greedy algorithm simply picks which one has the lowest energy. The important thing about greedy is that it makes purely local decisions. It does not consider the global impact. It does not track community costs like dynamic programming does, and never backtracks. At every step, it commits immediately to the lowest number it sees in the next row. Because of this, the algorithm is extremely simple and fast, but also much more short-sighted. The exact same idea applies to horizontal seams, except instead of starting at the top row, we start from the leftmost row and move across to the right, again choosing the lowest energy at each step. Now, Ryan will explain an example of how greedy algorithm works.
Thank you, Darius. So, as mentioned before, next slide. How the algorithm will work is by going row by row, then checking for the seam with the lowest energy. In this example, we can see that for the first row, the lowest energy would be the one with 3. From there, it will move on to the next row and check its neighbors. And the lowest energy, which in this case will be 3 as well. So it will just carry on till the end, where the path will end up being 3, 3, 1, 3. Next. The time complexity is similar to dynamic programming, while space complexity is slightly better than dynamic programming. Now let's look at our results. Next. We tested with a 60% reduction, removing over 1,000 seams. Here's the greedy output, and you can sort of see that the castle towers are warped and the person is unnaturally stretched. Compare this with the dynamic programming result, which maintains a natural appearance. The difference is quite clear to see, and from there, Adam will run the program for our greedy algorithm.
Okay. So let me rerun the program. Okay. After running the program, it's the same logic. So I'll choose the same image, the tower, select the greedy, select the seam, maybe do it into 110 to 800, which will take a bit more time compared to dynamic programming. As you can see here, it's the same process where it will seam carve the image, but it will just take a longer time for more precision.
All right, so now we'll be talking about why does greedy fail. The fundamental problem is that local optimization doesn't equal global optimization. Greedy can get trapped in high energy regions and can't escape because it only looks at the immediate next step. In this example on the screen, Greedy picks a path with total energy of 110, while the dynamic programming finds the optimal path with energy of 30. So each seam has a small error, but after removing 1000 seams, these errors accumulate into the distortions we saw. Next slide. So to directly answer the question, no, the greedy algorithm does not provide results comparable to dynamic programming. While it works for small reductions, it fails for large ones. For production applications, dynamic programming is essential. So now let's hop back to our application. Yeah, as you can see that it is done and our application runs perfectly with Greedy itself. So with that, we've come to the end of our presentation. Thank you.